The next presentation will be about, thank you, will also be a theoretical presentation. Péter Körösi Szabó, Domonkos Cifra, and Gábor Kovács from the Rényi Mathematic Institute. The first presentation will be about reviving the unreadable, AI-powered OCR for degraded documents in archives. The presenter will be Gábor Kovács, who is researcher at the Mathematic Institute of Sciences. And Gábor Kovács has a background in artificial intelligence, starting with work on AI solutions in the automotive industry. Over the past 3 years, he have been at Alfred Rényi Institute of Mathematics working on projects in natural language processing and document AI.
I would like to give a presentation about how can we enhance the documents which are at archives and which are pretty degraded. So the title of my presentation is Reviving the Unreadable, AI-powered OCR, or optical character recognition for degraded documents in archives. A couple of words about us. 3 of us working on this project, namely Domonkos Cifra, Péter Körösi Szabó, and myself. We came from the Alfred Rényi Institute of Mathematics, where we have an artificial intelligence group. We have a couple of theoretical research areas, for example, computer vision and learning theory, and a couple of applied projects, which one of them is about time series prediction for the energy sector and medical sector, and the natural language processing and document AI for Hungarian archives, namely the historical archives of the Hungarian State Security and the National Archives of Hungary. So the main goal with the archival projects is to integrate different kinds of AI solutions into archival processes. What I mean on AI solutions is mostly the latest advantages in AI technology, which is the large language models. And what kind of applications can we build on these large language models? I brought 3 examples, which I will introduce at the end of my presentation. The first one is a retrieval augmented generation based application. The second one is about sensitive data removal. And the third one is named entity recognition. But first, let me introduce the task and the challenges we have to work with. So the task comes from the data format we have to work with. When we want to build an application, for example, a retrieval augmented generation application, unfortunately need textual data. But at archives, we have document images. So in the first step, we have to read out the text from these document images. That's where the task optical character recognition what we have to solve. So the challenge comes from the quality of the data, which is that at archives we have quite degraded documents. Here you can see different kind of degradedness of the documents, one with a quite a good example, one with a moderate example, and one with a poor quality, which is quite unreadable. So why is it difficult to solve this kind of data domain? So I would like to give a short demo how state-of-the-art off-the-shelf OCR systems can perform this task. So let's take an original document, which is quite degraded, and check how 2 state-of-the-art methods, for example, Google's Gemini and Google Lens, can solve this task. As you can see, this is the here you can see the extracted text from the document. The green color is for where the OCR or the optical character recognition model could read out the text correctly, and the red where the extraction of the text is incorrect. And as you can see, the character error rate of the two solutions is around 25%, which means that 25% of the characters were lost or there were some problem when reading out it. And we can also check the word error rate, which is about 50% for both the models, which means that more than half of the words contain some kind of errors by these models. So it is worth talk a minute about where these kind of errors come from. And basically there are two sources of this error. The first one is the text detection module of these OCR solutions. Unfortunately, the text detection modules of these on these kind of highly degraded documents cannot really work well. So unfortunately, they cannot really detect the text lines of these documents. There are a lot of missing text, false positive bounding boxes, and so on. And even if we can find the text lines from the documents, the text recognition model, which task is to read out the text itself, cannot really solve the problem because it's unreadable most of the case. So how do we approach this problem? Basically, we found that there are two different kinds of approaching or main strategy. The first one is that we try to enhance the OCR system directly. So we can collect data which is specific or characteristic on this archival domain, which contains very degraded documents, or we can choose another architecture. For example, we can apply for larger models or changing the model type from LSTM to more sophisticated model types, for example, transformer. But another approach which we opted for is applying a kind of preprocessing step where we Okay, my GIF won't work, unfortunately, I don't know why. So where we try to enhance remove the noise from the documents, and we apply a preprocessing step on the image, and after that we can use our already available OCR pipeline. So our solution is standoff a document image enhancement model, which is about cleaning the document images itself, removing the unnecessary noise, and retaining only the text on the documents. The model architecture which we chose is a convolutional based UNet architecture. UNets are very good at image transformation tasks. The convolutional operations are great for filtering image, which is for removing different kinds of noise. And the skip connections in this architecture is great for training these models. So here I would like to give a short demo of our model. I don't know, can you click on the... No? Back? No? Does it work? Yeah. So you can come here and upload your own document image and test our model. But if you don't have any degraded document images, then we have uploaded a couple of examples. So if you click on any of the examples, it uploads to the model. By clicking on the enhanced image, the Hugging Face demo starts to remove the background, and you can check our solution on this kind of task. You can also increase the number of iterations, aka how many times our model runs on the same image. The higher the iteration number, the better the result. So feel free to check our model on your own data. Okay, a couple of words about the data, because since we are talking about machine learning models, we need to collect a lot of data on which we can train the models. So here I would like to mention 3 different kinds of tasks: the text detection, the text recognition, and document image enhancement. And for the text detection, we need to collect bounding boxes around the text lines. For the text recognition, we need to collect data where we read out the text from the documents. And for the document image enhancement, we need to create data where we have a cleaned version of a document and a degraded original version of the document. So there are 2 main approaches for creating this kind of data. The first one is human labeling, which in this case, unfortunately, is quite cumbersome. And for example, the document image enhancement task is extremely hard. But there is another solution, which is the synthetic data generation. In our case, for the text detection and the text recognition, it's quite an easy approach, while to the document image enhancement, it's a moderate task to solve. So what we have created is a synthetic data generation framework in which we progressively compile degraded document images. In the first stage, you can see that we put text on a blank paper. We can choose different kind of languages, layouts, and fonts. In the second step, we choose a random background image, which supports different kind of paper types. In the third step, we apply different kind of perturbations on the image. And in the third step, or in the fourth step, we apply different kind of geometric transformations and perturbations on the image. So here you can see a couple of examples as the output of our synthetic data generation. So our document image enhancement model gets these degraded documents and has to output this cleaned version of it. Okay, if you want to use this kind of framework for other tasks, we will make it available. Currently it's not, but how can you do it? First, you need to collect a corpus with on your own language, so a lot of text on your own language. If you want to train it on different types of fonts, for example, we were training it on typewriter text because our data contains a lot of text in that style, that you just have to upload a lot of different fonts into a folder. If you have different background images than our data domain, then you just have to upload into a folder different kinds of background images, and you have to collect different kind of noise images. For example, stamps, scribbles, or textures, which our framework automatically uses for augmentation for the documents. And you can handle it modularly. So we have also created an OCR, an optical character recognition model. We opted for a so-called TR-OCR model, which is a transformer-based model. It's quite state-of-the-art in this domain. And we have trained it on the Hungarian language and on our degraded archival documents. We collected a lot of, or created a lot of synthetic data for this task, and also collected or got a lot of human label data on this purpose. So how our current OCR pipeline is. Currently, when we get a document, our first stage is about cleaning its document using our DIE model, which removes the noise from the document image. After that, we normalize the orientation of the document image. We detect the text lines of the document image, and we perform the text recognition step which reads out the text from the image. So the evaluation of our solution. First, I would like to talk a couple of words about what happens to the state-of-the-art Gemini and Google Lens models if we apply the cleaning model as a preprocessing step. So as you can see, the original performance was around 25-23% for CER. But if we, in the first step, clean our document, we can achieve a much better result, namely 7% or 5%. But if we check our pipeline that our TR-OCR model achieves on the noisy document 10%, which is better than the 25 and the 22%. This is because we have fine-tuned our model on the degraded documents, and our cleaned our model on the cleaned document achieved 6% on the CER, which is somewhere between the good and the moderate on this spectrum. So another advantage of our model is that it's a local model, so we don't have to upload our data or documents through an API to some third-party model. We can use our models offline in the institute. About a couple of words about the inference time, at Rényi we use an NVIDIA server A100, which has 8 GPUs. Currently we use 2 GPUs and we can process 25,000 document images per day. So I would like to conclude my presentation with 3 different kinds of applications which we can build on after we have extracted the text. The first one is a kind of digital historian which builds on the retrieval augmented generation technique. In this case, a researcher has an API and he or she can perform semantic search on the archival database. And the machine doesn't only give a response or answer the question, but can also give summarization of the documents and can also return the relevant documents based on the answer was created. Another application is sensitive data removal. So in this case, we can remove different kinds of sensitive or personal information from the documents. And what is an advantage of building on large language models, that we don't have to predefine different kinds of keywords or categories on which we want to, or which kind of data we want to remove, but we can define using natural language different abstract concepts what to find in the documents, and it's quite flexible. The third and last application is about named entity recognition. So sometimes we want to recognize different kinds of named entities, for example, person names, location, or events. And we want to build a structured representation of these kind of information. And for example, graphs or database tables. And we can use this kind of data representations for different kinds of tasks. So that was my last slide. Thank you for your attention. And if you have any questions, I try to answer it.
We are unfortunately on time, but we have time for at least one question. Sven.
If I understood, you would also share the data. Are you using certain standards to share the data so that people can look at how to label the data and in what form to provide the data for training? And especially, are you using standards for that purpose?
Sorry, are we using standards? It's a kind of data generation framework which generates data on the fly. So we don't have a pre-generated data sets of a size. Labeled. The framework itself generates the data set. So it's a kind of generator or iterator in Python. You can use it in a PyTorch data loader. And what it generates, it's an input image and the metadata, which are the labels. For example, the text, the bounding box around that, and the layout and etc. So you can extend it. But if you just start the program, it starts to generate out of nowhere the data, and you have almost limitless or yeah.
Okay, understood. Yeah, thanks.
Okay, thank you.